what we're going to do in this short activity here is go through a derivation of some kinematics equations. So we've been spending some time solving problems related to the motion of objects using graphs. We've been drawing motion graphs based off of a word problem, and then we've been using that motion graph to analyze the situation. And all of that's good and useful, but it would be nice if there was a quicker way that we could do that. And so that's what this is going to be. Is we're going to derive a quicker way. We're going to derive some equations that we can use for a lot of different situations, so we won't have to necessarily draw a motion graph every single time we want to solve something. So we're going to use a motion graph here to actually go through this derivation. So the first thing we want to do is draw the velocity versus time graph for an object speeding up with a positive velocity, but not starting from rest. So go ahead and try and do that. Maybe you want to pause the video briefly so you can try and do it on your paper first before I go through it. Okay, so what that should look like is we should have a line here starting with some positive velocity and then speeding up, going away from our x-axis, just a straight line with a positive slope. Now we're going to get into the derivation part. So we're going to be told in each of these situations what things we know and what things we're looking for. So in this first situation, we're looking for a displacement of the object, and we're told here that we know the initial velocity, the final velocity, and the time. So what I want to do is I'm going to go ahead and label those quantities on my graph. So my initial velocity is going to be this right here. My final velocity, and I have to extend my graph a little, is going to be this right here, and I also know my time. So what I'm looking for is my displacement. So again, maybe pause the video and think about how you can find that displacement from this kind of graph. Alright, now you've had a chance to try it. The way we're going to find the displacement is we're simply going to look for the area under the curve. And I'm going to break this into two different shapes. I'm going to have a rectangle here and a triangle here. So I'm going to say my area is base times height. So for the rectangle there, it's going to be VI times T. So that's area 1. Area 2, the triangle, is 1/2 base times height. So that's going to be 1/2. And I have to be a little bit careful here because my height is simply from the initial to the final, okay, which is actually a height of VF minus VI. And my base, though, is still that full-time T. I'm going to take these two down here and add them together and do a little simplification. So my total area, which is my displacement, is going to be VIT plus 1/2 VF minus VI times T. I'm going to go ahead and multiply out that term to simplify it a little bit. So what we're left with here is delta x is equal to VIT plus 1/2 VFT, again multiplying the 1/2 times VF times T, and then also the 1/2 times VI times T, so minus 1/2 VIT. I see that I can combine these two terms, so what I'm left with is delta x equals 1/2 VIT plus 1/2 VFT, and I'm going to rearrange this slightly, factoring out the 1/2 and putting the t at the end, and this is really just the style that we're writing this equation in. But I end up getting 1/2 VF plus VIT. And that right there is going to be our first kinematics equation. So in any situation, we can use this equation, and that's going to allow us to analyze the motion of an object. We don't need to worry about drawing a motion graph every single time. So for our next one, we want to write out our equation for the final velocity if we know our initial velocity, VI, our acceleration, and our time. So once again, I'll give you a second to pause the video and think about this one, and then I'll go through the solution momentarily. So what I would focus on here is the fact that the acceleration, which we know, is our slope. So the slope of this line is equal to a. So that's where I'm going to start here. So we can say that the slope, which is a, is our change in y over our change in x. I'm going to label some points here. We have the point 0 vi. And this point I actually know because I do know that I'm looking for this final velocity. That's the quantity I ultimately want to solve for. But I'm going to say that this final point is t comma vf. So I can say that a equals vf minus vi over t minus 0, which you should recognize here actually as our formula for acceleration. And that's one way to actually derive that formula. I know we've already used that one, but we could derive it from a graph. I'm now going to solve for vf, so I'm going to do a little rearranging here. So I'm going to multiply both sides by t, and so I get a times t, because that 0 just goes away. A times t equals vf minus vi. So when I solve for vf, I'm going to get that vf is vi plus at. And that is going to be our second kinematics equation. For the last one here, we want to write another equation for the displacement if we know initial velocity, acceleration, and time. So, we're going to start with the things we know. We know vi here, we know our time, and we also know our acceleration. So we saw from the last one, that means we know that our slope equals some acceleration a. And we ultimately want to find our displacement. So once again, I'll give you a chance to do this on your own, so go ahead, pause the video, try this one, and then we'll go through it. So the thing we want to focus on here is that our displacement, once again, is going to be this area under the curve, which we once again can split up into two parts, and we actually already have an equation for it. We found that in the first part that delta x is 1/2 vf plus vi times t. Well, the problem is this includes this variable vf here, and we don't have vf. We're not given vf. All we're given is initial velocity, acceleration, and time. But we are in luck because we actually just did another derivation when we found vf, and we found that vf is equal to vi plus at. So what I'm going to do is I'm going to go ahead and actually combine those two equations. Both of them come from the graph, but I'm not going to necessarily go through re-deriving them because I've already done that. I'm just going to combine these two kinematics equations that we've already talked about. Okay, so we're simply taking these two guys and putting them together. So I'm going to say delta x is 1/2. Instead of vf, I'm going to write vi plus at plus vi, which is the other part of the equation right here. And that entire quantity is multiplied by t. So I can simplify this a little bit, and so I'm going to have delta x equals 1/2. I'm going to combine the two vi terms, so 2vi plus at all times t. And then I'm going to distribute both the 1/2 and the t to each term. And so I get delta x equals 1/2 times 2vi times t just gives me vit. 1/2 times at times t gives me 1/2 at squared. And that there is my third kinematics equation. Now there is a fourth one in addition to the two we've already gone through. That one says vf squared equals vi squared plus 2a delta x. Okay. And that comes from eliminating time from the equation, combining other ones. And we're not going to go through that derivation. It's a little bit messy. But you certainly, if you've enjoyed this, you're certainly welcome to do that on your own time. But you also could just take my word for it that that's what that equation is. So there we have it, our four kinematics equations. We're going to actually look at applying them some more in class in a little bit.